Okay, thanks. Right, so this clique-independent set, it's an old problem in two-party communication complexity. And this is a standard textbook for the subject. The problem's defined already on page 6 of the book. So, very fun problem. You have two players that are communicating over a shared communication channel. And this is the problem that they're supposed to solve. The problem is defined relative to a graph. So you fix a graph on n nodes. I just think of the nodes as the numbers from 1 up to n. And as input, once the graph has been fixed, as input, Alice is going to get a clique in the graph, so a set of nodes spanning a clique, and Bob receives an independent set. And the question is just, does the clique intersect the independent set? This is the communication problem. So, because any clique and any independent set can only intersect in at most one node, I can sort of cleverly say that what they're supposed to do is to compute the size of the intersection, which is just 0 or 1. So here I'm defining a Boolean function. So this seems like a fun problem, but it was in fact introduced in a very serious context. In Yannakakis' work, where he was studying the complexity of expressing combinatorial optimization problems as linear programs. So his vision was to show that you couldn't express, say, the traveling salesperson problem as a polynomial-sized linear program. And in connection to this study, he found this clique-independence problem in connection to the complexity of expressing what are called vertex packing polytopes for this graph G. So vertex packing polytope is just the convex hull of the characteristic vectors of all independent sets. And this is a long story, this so-called extension complexity work. For example, there was this recent breakthrough that finally completed Yannakakis' vision of showing that many natural polytopes can't be expressed as polynomial-sized programs. This was the original motivation, but it has been. The clique-independent set isn't really related to that necessarily. Okay, so this was the original motivation, but I'm going to leave this aside and just focus on the problem at hand. So maybe the first trivial observation about this problem is that, okay, it's a special case of the set intersection function, which admits efficient non-deterministic protocols. So if you haven't seen non-deterministic communication before, the model is very simple. Here, Alice and Bob, they don't communicate at all with each other. All they do is they just guess a proof string. So if you want, this proof string appears from the sky. The length of the proof string is important. It determines the cost of the protocol. And then Alice and Bob independently check whether they want to accept or reject the proof. So Alice would look at her own input. Okay, in this case, it's a clique in the graph, and the proof string. Bob would look at his own input and the proof string. And both would say independently of one another whether they want to accept or reject the proof. So we consider a particular proof as accepting if both players accept it. So, as usual in a non-deterministic computation of a function, for yes inputs, for one input, there should exist a proof that both players accept, but on no inputs, no proof should be accepting. So here I'm just writing the basic fact that there's an efficient non-deterministic protocol where the proof string is thought of as the name of the node in the intersection. So there are n nodes, you take log n bits to write down the name of a node in the intersection. So I'm using the clever notation of borrowing just a complexity class from classical Turing machine literature, so NP stands for non-determinism, and just writing CC, the superscript, to say, think of the communication analog of non-determinism. So this is pretty canonical. However, something more interesting about this problem is that it also admits
the element in the intersection. They both can check, is this element in their respective features independent set, and they just output, do they agree?
Right. So this is even true for the set intersection problem. That it has it. Okay, so Yannakakis was interested also in the complementary problem of trying to certify that the clique and the independent set are disjoint. So this is a harder problem, but it's not terribly hard because of the underlying structure of the graph. So he was able to show that if you want to certify that the two sets are disjoint, you can still do it rather efficiently with just a polylogarithmic number of bits of communication, which in communication complexity is usually thought of as efficient. However, still a small gap in that we don't know whether there are graphs that require more than log n conondeterministic communication. So this was Yannakakis' question. It was originally related to the extension complexity question. Do there exist graphs that require more than log n conondeterministic communication? Now I should say the original motivation has sort of sailed past because we have good lower bounds for that problem already. But luckily there's a different motivation for studying this question, as if the communication question itself wasn't interesting enough. So there is this conjecture in graph theory called the Alon Saks Seymour conjecture, which asks about the relationship between the chromatic number of a graph and the bi-clique partition number. So the bi-clique partition number is just the minimum number of bi-cliques, bipartite complete graphs, you need to partition the edges of the graph. So in other words, you want to express the graph as the edge disjoint union of bi-cliques. What's the minimum number of bi-cliques you need? Well, that's the bi-clique partition number. And it's a theorem that if G is the complete graph on n nodes, then this inequality holds with equality. So the chromatic number is n, and it turns out, this is a non-trivial theorem, that the bi-clique partition number is n minus 1. So these people thought that, okay, if this holds for the complete graph, surely it must hold for all graphs, or something like this. This was the original motivation. And the conjecture was made in the early 90s, and it stood for some 20 years, after which Huon and Sudakov managed to disprove this. So they exhibited graphs where the chromatic number was polynomially larger than the bi-clique partition number. Okay, however, this counterexample still leaves open whether the chromatic number might be reasonably bounded in the bi-clique partition number. So namely, we can look at this relaxed conjecture of asking whether the chromatic number might be polynomially bounded. So if I call this the polynomial Alon Saks Seymour conjecture, then this is something that was studied recently in previous work, and there's a beautiful connection. It turns out that these two questions are exactly equivalent. So one of the directions, the easy direction, was shown earlier in unpublished work of Alan and Haviv, and these Bousquet and others, they recently did the other direction. Now, the punchline in this current work is that both of these questions or conjectures are false. Now, this is not that surprising maybe because people were conjecturing that this happens anyways nowadays. But anyways, the main theorem in this work is just that there does exist graphs where the conondeterministic complexity for the clique-independent problem is larger than, or asymptotically larger than log n. Or if I phrase this in the language of the Alon Saks Seymour conjecture, it means there are graphs where the chromatic number grows larger, grows faster, or superpolynomially in the bi-clique partition number. And well, you can compare this to some previous work. So, for example, this Huon and Sudakov result in the language of communication complexity says that the conondeterministic complexity is just some constant larger than 1 times log n. And this has been improved a little in recent years. But now the truth is that there are graphs where the complexity might be super logarithmic. Okay, so the way we're going to prove this is using a very different approach to what had been done in previous work. So I would say the previous work has done very direct attacks on the problem, whereas we take a more indirect approach. And in some ways, the proof strategy is kind of obvious in hindsight. It's used before. The idea is that you don't attack the communication problem directly, but you define an easier to analyze query complexity problem. You study that, you give bounds there, and then you transfer the result over to communication complexity. And this strategy is exactly what's being employed to give the best lower bounds we currently have for the log rank conjecture of Nissan and Victorson, just for example. Okay, so I want to flesh out this proof strategy. So I like to think of communication complexity as the study of the complexity of representing Boolean matrices. So whenever I'm given a two-party function, I can visualize it through its communication matrix. It's just that truth table is the function where the rows are indexed by Alice's input, columns are indexed by Bob's input. So then this brings about a combinatorial way of looking at protocols. So for example, these non-deterministic protocols, they're nothing but coverings of the one entries of the communication matrix with rectangles. So it's not hard to see that in a non-deterministic protocol, these proof strings, they are in one-to-one correspondence with combinatorial rectangles. And so then, in fact, the non-deterministic communication complexity is just the logarithm of the minimum number of rectangles you need to cover the one entries. So in this covering, you might have rectangles that overlap, like here. It only means that on that particular input, there are many different proofs that make Alice and Bob accept. However, if you think back to the clique-independent set problem, the canonical protocol we gave, where you guessed the name of the node in the intersection, it has this additional property of being unambiguous, in that on any input there is at most one accepting proof, namely the name of the node in the intersection. So really, for the clique-independent set problem, the picture doesn't look like this, but more like this, in that the proofs are unique or unambiguous. Combinatorially, the rectangles do not overlap. Now, this is kind of a fundamental property of the problem, in that kind of the converse holds. In that whenever you have a picture like this, whenever you have a two-party function with an efficient, unambiguous protocol, you can efficiently embed this as a clique versus independent set problem on some graph. So in other words, the clique versus independent set problem is complete for unambiguous communication. So this was already observed by Yannakakis, that whenever you have a covering of the one entries with disjoint rectangles, you can efficiently convert it into a corresponding graph then. The conversion is just you take the rectangles to be the nodes of the graph, and two nodes or rectangles, they're joined by an edge if the corresponding rectangles share a row. So that's what I've done here in this conversion. And on this graph, you can find this original problem as a subproblem. That's just because Alice can map her input, which is a row, to the set of nodes or set of rectangles that intersect this row. So by the definition of the graph, this will be a clique in the graph. And similarly, Bob maps his input, which is a column, to the set of rectangles intersecting his column. Again, by the definition of graph, this will be an independent set. And the independent set and the clique, they intersect if and only if the original input was a one input, it was covered. Okay, so what this all means is that I'm really taking this picture as the starting point. That I'm interested in just any two-party functions, and I can write its unambiguous communication complexity as logn for some graph on the number of nodes, which is exponential in the unambiguous complexity.
I mean, if it was true, it was. But if it was true, well, this is like an NP measure. Right?
Yeah, this will measure.
Right. What's
Right.
another code?
Yeah, this
Not quite. I mean, so this is just saying that you can take any function and starting from that, you can define a graph. So from this, this function, you get some n, which is related to the unambiguous complexity like this. I think there's only one n in the picture now, which is the number of nodes. It's not...
So suppose the projective you're talking about was true. Would it imply that for every function f, up of f is order of log n? If it was true?
Say that again?
You are about to show that it's false, but if it was true, would it say that for every function f, up of f is not order of log n?
No, that's not related. I mean, like that's also probably false because like UP is a subclass of NP. We believe there's our functions which have large NP. I mean, this is just saying that if you have small UP complexity, then you can reduce it to clique versus independent.
But suppose you could solve the clique versus.
No. What that conjecture is about is what is the coNP complexity of clique versus NP.
Right, so I mean, I can read...
So UP is a subclass of NP. And it's a question of what is the difference between UP and coNP.
Yeah, so I can exactly rewrite the Alon Saks Seymour conjecture now in terms of just UP complexity, which is, so here I've restated the theorem. So the Alon Saks Seymour conjecture would say that the conondeterministic complexity is always linear in UP complexity, but my theorem says there exist functions where there is a polynomial gap. Right.
So if you replace UP with NP in this statement, what would you go for?
Okay, so it's trivial to separate NP from coNP. Set disjointness. And there's an exponential separation. However, there can never be more than a polynomial separation with these guys because of Yannakakis' upper bound. So the separation can at most be quadratic. Okay, so this is still a communication problem, but now it becomes kind of obvious what the query complexity problem should be. So you just define the decision tree analogues of these two measures. So in the query complexity world, you would be dealing with just plain Boolean functions without any Alice-Bob two-party structure. And you would be interested in the conondeterministic decision tree complexity of a function and its unambiguous decision tree complexity. What are these? Well, non-deterministic decision trees, they're nothing but collections of certificates for the function, one certificates. So partial assignments to input that force the function to be one. So really, a non-deterministic decision tree, it's essentially just a DNF. It's a disjunction over conjunctions. And the complexity measure is then just the DNF width. And okay, canonically, the conondeterministic complexity is the DNF width of the negation of the function, which is just the CNF width. And I also call a decision tree or a non-deterministic decision tree unambiguous if there is at most one certificate or one term that is true on any input. So if you want to think of this combinatorially, it's like an unambiguous DNF, it's covering the one entries of your Boolean function with subcubes that are disjoint. So the complexity always the width of the terms, the number of literals in a term. Sorry?
You can only do 3CNF if you add variables.
Right. So the agenda is just that we're going to give a proof of this query complexity separation. That's one step. And completely disjoint from that, an independent step, which is we convert the query separation into a communication separation. And crucially, for the second step, we're using some previous work, and I get to advertise that work a little bit too. Well, I mean, talks about Boolean functions. This is about two-party functions. So there's a non-trivial transformation you have to do there. Yeah, spoiler alert. But okay, I'm going to start with the query thing. So first, we're just going to forget about communication and try to give a separation between unambiguous complexity and conondeterministic complexity. Well, it's very easy to give some function with some gap. So here's an example. You define a Boolean function on 3 inputs, and you say we have a 1 input if the Hamming weight of the input is either 1 or 2. Now I claim that the unambiguous decision tree complexity is 2, because you can write this function as the following DNF with terms of width 2, and I claim it's unambiguous. So on any input, at most one of these terms can evaluate to true. However, the conondeterministic complexity, the complexity of certifying 0 inputs, that's 3. So you can see that by just looking at the all 0 input, 0, 0, 0. So this input is fully sensitive. If I flip any one of the zeros to a 1, the function flips from 0 to 1. So there's no certificate for this all 0 input that doesn't read all the variables. If you don't read all the variables, I can still change the value of the function by flipping the variable you didn't read. So usually when you're dealing with trying to separate query complexity measures, you're quite often done after you've found a single example, because the standard trick is that you take your function and you start recursively composing it with itself. So here's my f with 3 inputs, and I'm just going to take 3 copies of this function and plug them again as inputs to a copy of f. So the second level of the recursion would look something like this. And more generally, I would define the function according to like a complete ternary tree, where the internal nodes are computing f, and everything's a tree, so the inputs are disjoint. And so the idea here, the hope, is that if f exhibits some gap, 3 versus 2, maybe when you recursively compose it with itself, every time you do add one layer, the gap would increase by a constant factor. So, something like this. This is the hope. And this works beautifully in some settings, like what I've described here is exactly how you give a separation between Fourier degree, the polynomial degree of writing f, versus its decision tree complexity. It turns out you get a polynomial separation like this, but here it doesn't work. And the problem is that the complexity measures we're interested in, these non-deterministic measures, they're inherently one-sided. They don't play well with recursive composition. So, intuitively this is because, suppose I want to certify that the top gate here outputs a 1. So this is supposed to be easy, right? Easy to certify ones. But maybe a certificate for the top gate outputting a 1 needs to certify that some of the inputs to f are zeros. So the only way of then certifying a 1 would be to recursively certify that some of these f's are outputting zeros. But inductively this is supposed to be hard. It's supposed to be hard to certify that an output is 0. So this is kind of intuitively why this is difficult. Now I still want to use recursive composition in my construction, but we need to overcome things like this. So one solution to this problem is, instead of looking at Boolean functions, I can enlarge the input-output alphabets of our functions. So I'm going to consider functions that are now, instead of Boolean, I still have this hard-to-certify symbol 0, but instead of just the symbol 1, I have now many symbols in this set sigma that we think of as easy to certify. So the intuition is that if I take a function like this and I start recursively composing it with itself, then I don't run into trouble. To certify that the top gate outputs a sigma, which is supposed to be easy. Maybe I've designed F such that certificates for this only read sigma symbols from the inputs. So then I only recursively need to certify statements of the similar form. So in other words, my certificates for a sigma output, they never contain zeros. So recursively, I never need to certify zeros. Okay, so this is abstractly the approach, and I'm going to give you a concrete example of an F that starts working. I should also say that what I've talked about here is how the recursive composition makes the unambiguous complexity small. I still need to make this function compatible with arguing that the conondeterministic complexity is small. And what the property I'm going to use is that the conondeterministic complexity is witnessed by the all zero string. Okay, so you're going to see that later on. Okay, so let's construct this function. Now, a key observation with unambiguous decision trees is that if you take any two certificates from an unambiguous decision tree, it must be that these certificates intersect in variables. I mean, if this didn't happen, if you had disjoint certificates, it would be easy to construct inputs that satisfied both the certificates. And this would contradict unambiguity. So when you want to construct functions with efficient unambiguous decision trees, you need to have the certificates always intersecting. So then if you want to draw your unambiguous decision tree as a kind of a hypergraph, where the nodes are the input variables, and for each certificate you have an edge corresponding to the variables that are involved in the certificate. So these are the hyper edges. Then the set of edges is pairwise intersecting. That's just a structural property you need to have. And then, okay, if I'm asking you to think of interesting examples of pairwise intersecting set systems, you very quickly think of finite projective planes. And these are exactly the things we use here as a kind of a template for defining this function. So this one here is the simplest non-trivial example of a finite projective plane called the Fano plane. 7 nodes, 7 edges. Each edge contains 3 variables. So to define the function, I need to... So I'm going to start by assigning for each node, or an input, an ordering of its incident edges, just for technical convenience. So each node assigns numbers 1, 2, 3 to its neighbors. And I should mention, a little later I'm also going to use this additional property which I have here, which is if you look at each edge, you can find the numbers 1, 2, 3 from it. So you can also think of each edge as ordering its incident nodes. Okay, so this comes a little later. Now it's just important that each node has an ordering of its incident edges. So then I can say that the inputs to my function are from this alphabet of there's a 0 symbol, or then numbers 1, 2, 3. 1, 2, 3, these are the sigma symbols that are intuitively easy to certify. So the symbols 1, 2, 3, they correspond to pointers. So if a node has value I, it just means that the node points to its ith incident edge. That's my terminology. If a node receives the value 0, that's a special value. That just means that it's a null pointer. It's not pointing anywhere. Okay, so now I'm ready to define this function. I call, if I fix an input, I call a particular edge of the hypergraph satisfied if all of its nodes are pointing to that edge. So the function is just, the function evaluates to 1 if there is a satisfied edge. So all of this is quite canonical. I automatically have an unambiguous decision tree of cost 3 now for this function, because the certificates are just in one-to-one correspondence with the edges. The certificate just checks that all of its nodes are pointing to it. And of course it's unambiguous because for any pair of edges, they intersect somewhere. and in the intersection there's a node. The node can point to at most one of its incident edges. So you can't have two edges be satisfied simultaneously. Okay, so there's a subtle problem with this construction, which is that even though the unambiguous complexity was 3, it's still too easy to certify 0 inputs, in particular this all zeros input. So now the subtle point is I need to prove that the all zero input is hard to certify. That plays well with the recursive composition. If you think of having all zeros input at the bottom of the construction, you're going to have all zeros all the way up. So a good property to have is that the all zeros input is hard. But it's not yet. Because to certify that this evaluates to 0, there are no pointers. You can pick any edge and query all its variables. So the bottom edge, for example. That certifies that the function is evaluates to 0 because no edge can be satisfied. Every edge intersects the bottom edge in particular. Okay. So the solution to this problem is I'm going to add weights to the inputs. So now, if you want to find out where a particular node is pointing to, you need to spend more than one query for it. So each pointer value is now encoded with a group of 3 variables in this case. And the encoding is given by some gadget, some function g. And the important thing about the encoding is that if you want to find out whether the ith pointer is there, you need to spend I queries. If you want to find out whether a particular node is a null pointer, you need the maximum number of queries, which is 3. So the specification here is important. It's not so important how we actually do this encoding. For concreteness, here's one way you could do it. So this is like a truth table for this function g. So just to see, to check whether a particular group of variables represents the value 1, you only need to query the first position. For the pointer value 2, you need to, in the worst case, you need to query 2 different positions. Okay, so now this works. Now we have a gap. So with these weighted inputs, the unambiguous complexity now is, so let's look at, for example, the bottom edge here. The bottom edge, it's canonically again checks that the first pointer is there, the second pointer is there, the third pointer is here. So that the cost is just 1 plus 2 plus 3. And here I'm using the fact that for each edge, I have the numbers 1, 2, 3. So that the ordering I used was this balanced or symmetric. Okay, so the unambiguous complexity is 6, but I claim that the conondeterministic complexity is 7. One more. Crucially on the all zeros input. So on the all zeros input, it just means that there are no pointers anywhere, but to certify that there are no satisfied edges, you need 7 queries. And I'm just going to sketch this argument. The crucial thing about my weighting I chose was to ensure the following amortized complexity property. I claim that you need, if you want to certify that a particular pointer is not in the input, you need, in an amortized sense, you need at least 1 query to do so. If you want to certify that some set of I pointers aren't there, you need I queries. And that's exactly what the weighting function is doing. If you want to find out whether, okay, so let's say, how many queries are you going to make to these underlying nodes? If you make 1 query, you can only know that, okay, the first pointer wasn't there. But you don't know about the second and the third yet. If you make 2 queries here, you know that the first and the second pointers aren't there. So you're always paying, in an amortized sense, 1 query to disprove a particular pointer. So then, it's just an easy counting argument. There are 7 edges. For each edge, you need to at least spend 1 query to disprove that one of its nodes isn't pointing to that edge. Okay. Now it might be a bit mystical. Why did I get this gap? but it's maybe more clear when you think of larger hypergraphs. So you let the size of these edges be k. Then the unambiguous complexity is just the sum of the numbers from 1 up to k. That's k squared over 2. But there are k squared edges. So there's a factor 2 gap asymptotically. And it so happens that already with this finite example I get some gap. So actually if you want to optimize this construction, you don't want to use too large finite projective planes. The optimal size is something like choosing order 7 planes, in which case the conondeterministic complexity turns out to be 57, the unambiguous complexity turns out to be 36, and they're related by this magical exponent that appears in the main theorem. So this is sort of explaining where the exponent is coming from. Okay, so this is now ready for the recursive composition step. I should also mention that even in the recursive composition step, there's one additional idea that is needed. Because what I've now described is just a function that outputs either a 1 or a 0. But recursively, I need my functions to be outputting pointer values to the upper levels. So there is this additional step where you need to convert a function where you assume 1s are easy to certify, 0s are hard. And convert that into a function where you have a whole set of easy to certify values, but 0 still stays hard. So I'm just going to leave this as for the interested reader to look it up. Sorry? This construction, not quite. It's a bit ad hoc. Okay, so instead of that, I want to focus on the second step. So we now have this query separation, and how do we transfer it over to communication? Well, luckily there's this other recent paper that is joint work with Charles Lovett, Raghu Megha, Thomas Watson, and David Zuckerman. We call it rectangles and non-negative hunters. So we're trying to actually include the main technical result of the paper in the title. Forget to advertise this a little bit. So the second step is just an application of something we do in this paper. Yeah, it's true. I mean, I didn't address this, but if you had you can only have trivial functions like that. If you have functions where the one certificates only contain ones, then it's only like the AND function that you get. So for any non-trivial functions, you need to certify both zeros and ones from the inputs. Right. So I mean, if you have two certificates that only read ones, they're automatically compatible. So you can't have more than one certificate, and then this is just a trivial function. Okay. So yeah, I'm just going to briefly describe the main result here and how I'm going to apply it. So this work, it's all about composed functions. Sorry? No, sigma will be finite.
I mean, like, so sigma in your example depends on it grows with the graph.
Right.
But if you fixed sigma beforehand, it's like 5, and the graph would be...
Well, sigma, in my example, the concrete funnel plane example, it was just 3.
Okay, so can you recurse the alphabet increases or not?
Actually, it will increase in the construction, but it's due to the part I didn't describe. So, yeah. Of course, by the way, again, something I didn't really mention explicitly is, even if the alphabet size grows a lot, it doesn't going to cost us anything, because at the end you could just encode everything in binary, and that's just an additional logn term somewhere. Okay. Right, so composed functions. This work is about trying to understand the communication complexity of composed functions. Most functions you study in communication complexity are composed functions anyways. The idea is you start with a plain Boolean function on n inputs, well, exactly the kinds of functions we were just constructing. And you want to somehow transfer this function, convert it into a two-party problem. And the canonical way, the standard way, is just to take each of the inputs to the, what I call the outer function now, and figuratively split the input into two parts. Give some bit to Alice, the other part to Bob. And concretely, this is achieved by some combining function g, which I call a gadget. So set disjoint is of this form. You have a big OR of a bunch of little ands, but more generally you can consider the gadget to be maybe a bit more complicated, taking b bits from each player. So then Alice and Bob's input, there would be this b times n long binary strings, where the inputs then are naturally partitioned into n blocks of b bits each. And obviously we'd like the gadget to be sort of complicated to compute, but still small. If g is complicated, intuitively you don't really know what the output of the gadget is before you communicate enough information about the corresponding inputs. So if you had a protocol of cost d, intuitively these d bits that you communicate, you can only really reveal d many of the output of the gadget. Which d? Well, that depends on the protocol. The protocol can decide where to spend its d bits. And that's like emulating a decision tree. And this is what we're trying to formalize. And with an appropriate choice of how the gadget be the inner product gadget on some log n bits per party, we're trying to say the communication complexity of these composed functions should be explained by some query complexity measure of the outer function. And this is what this main theorem in this paper is formalizing. So for this, to formalize this intuition, we're going to use this concept of conical juntas. These are kind of non-negative analogues of polynomials. So junta is just a function that depends on a few of its inputs. So d junta depends on d of its inputs. And a conical junta then is just a non-negative combination of these juntas. Well, okay, each junta you can express as a non-negative combination of just d conjunctions. So the whole thing is just non-negative d conjunctions. So here's an example. It's almost like a DNF formula, except now each term is weighted by a positive weight, and you're taking sums. So that the main theorem in this work says that you can take a randomized protocol for the composed function, and from the protocol extract a conical junta representation for the outer function. So randomized protocol and from that you can derive a conical d junta h, such that somehow this h records for each input to the outer function the acceptance probability of the protocol. So now I have to be careful. So the protocol, its domain is different from that of the outer function. So the protocol gets these two-party encodings of z. So each z is encoded by the gadgets. And for each edge there are this huge set of possible encodings for it. Each z might be encoded in exponentially many different ways. So when I say that the junta records the acceptance probability on z, I'm really making this identification that for z I associate with it the uniform distribution on its two-party encodings. So I feed the protocol a uniformly random two-party encoding of z, and I ask, what's your acceptance probability? Now, so this probability is taken over both the choice of the input and the internal randomness of the protocol. And the main theorem says that this probability you can record in this conical junta object. So for example, if this was a bounded error randomized protocol for the composed function, it means that whenever z is a 1 input, the acceptance probability is very close to 1. And when z is a 0 input, the acceptance probability is very close to 0. So from such a protocol, you would get a conical junta that pointwise approximates your outer function. Now, theorems like this have been proved previously, and I should mention it's a very long line of work that does this for polynomials. So when h is a polynomial. So starting with Rasborov, so works by Cherstow's pattern matrix method, and the polynomial approximation method of Zienzu, and so forth. But somehow polynomials, it's a kind of a powerful model of computation. So for starters, there are root n degree polynomials that pointwise approximate the end function, which doesn't make intuitive sense to me. Apparently, this is the truth for some quantum protocols, so that's fine. But I want to understand classical computing, and these are non-negative versions of polynomials. They behave more intuitively. So, in particular, for the AND function, you need, as your intuition tells you, to read almost all of the inputs to approximate it. And okay, this is a nice example illustrating that these are the conical juntas are really a weaker object. But sorry? So the question is what? Okay. So it's defined perfectly in analogy to what approximate degree is. So approximate degree is the minimum degree of a polynomial that pointwise approximates your function. Pointwise to within, I don't know, 1% error, additive error. And this is the same thing here. So the minimum degree overall D juntas, conical D juntas. Okay, so this is the degree. Right. So, okay, there are even more dramatic gaps between polynomials and juntas if you consider partial functions. Philosophically, the most important distinction is that polynomials are inherently two-sided. So polynomial degree doesn't really care about whether I ask it of a function or its negation. Okay, same degree. But in this world, it's more one-sided. And that's why we can use this to characterize the non-deterministic communication complexity of a function. So directly out of this structure theorem, you get a simulation theorem for non-deterministic computations. You can relate exactly the non-deterministic communication complexity of the composed function with its non-deterministic decision tree. And you have this additional term, which is just the size of the gadget, which we take to be logn. And it's sort of, the junta theorem, it's sort of overkill for this, because what the junta theorem says is that if you view this non-deterministic protocol here as a randomized protocol, so that means that on no inputs, the non-deterministic protocol accepts with probability 0. But on yes inputs, it accepts with positive probability, maybe very small, but positive nonetheless. So if you can write this acceptance probability as a conical D junta, then it looks something like this. This is a junta, conical junta, that on 0 inputs evaluates to 0, on yes inputs evaluates to something positive. So of course you can just throw away all the positive coefficients, turn the sums into disjunctions, and then you have a DNF representation for your outer function. So these conical juntas, they are the truth for non-deterministic computations. Now, so this is how you transfer lower bounds for decision trees, lower bounds for communication. The upper bounds are just trivial because a communication protocol can always just simulate a decision tree. I mean, whenever a decision tree queries a particular input to the outer function, you just spend b bits to communicate all information about the corresponding gadget. So in particular, we were also interested in the unambiguous complexity, and for that we only need the trivial fact that the upper bounds translate, that the communication protocol can simulate a decision tree. So these two, they're enough to just transfer the gap for query complexity over to communication. And interestingly, this should essentially be an equality, but I don't know how to prove it. But luckily, I only need the trivial direction here. Okay, so that's it. I also want to mention that this Hunter theorem, this is just a baby corollary of it. So in that paper, we're really interested in genuine randomized protocols that, well, for models that are simply characterized. So we get these sorts of simulation theorems not only for non-deterministic computations, but for many models that are characterized using like known lower bound techniques in communication complexity, like corruption bounds, versions of discrepancy, and so forth. But that's just a small advert. So, yeah. So let me just end with some open problems. You know, I conjecture that the true gap for these two measures is quadratic, and it should already be the case for decision tree complexity. If you prove it for decision tree complexity, you automatically get roughly the same results for communication. However, maybe it's a bit difficult to get large, close to quadratic gaps, simply because any gap you give for these measures is automatically going to get the same gap for Fourier degree versus decision tree complexity, for which the best gap we know of has this exponent 1.6 or something. And this has been the best for decades. So it's a bit discouraging, maybe. Also, I really like these simulation theorems. They just reduce communication questions to simple query questions. So can we give new simulation theorems for models like bounded error and noise computations? And the problem with exactly capturing this is just that it's a messy model. It's not simply characterized. But it shouldn't be terribly difficult, fundamentally. So it just means that, that this theorem holds, but with the appropriate model in place. Do you exactly characterize the communication complexity? Right, and one ugly thing about our Hunter theorem is we need to assume this block size of the gadget to be log n, which it always yields functions that are slightly unnatural, so you can't really apply it to functions that people have considered before. However, if you could prove the same theorem for block size a constant, that would be amazing. You would immediately give a new lower bound proof for the complexity of set disjointness, and you could pretty much go over previous works and just reprove them using just like a query lower bound. Okay, so thank you very much.